Hello guys, and welcome back to my channel. This is the number one channel for structural insight and a place where you learn, build, and innovate. So today I want to start the design of compression member, and this is the design of steel to BS 5950. So I want to do the introduction, and then after the introduction, I will tackle one example. So when I'm talking about compression member, I'm talking about the stanchion. This is the stanchion. The stanchions. So these are the steel compression members. Are steel compression members. And includes struts and column. So some of you may not be able to differentiate between the struts and the column. So struts and column are two different terms. So let's begin by struts. So what is a struts? The struts is a member subjected to a direct compression only. So a member subjected to a compression only. And what about column? So column refer to a member subjected to a combination of compressive loading and bending. So it refers to a member subjected to a combination of compressive loading and bending. So this is all about the struts and column. So struts and column differ fundamentally in their behavior under axial load depending on whether they are slender or stocky. So the column can be either slender or stocky. So another word for stocky is short, like that. So it can be either slender or stocky. So most steel struts and column can neither be regarded as slender nor stocky, but as something in between. Stocky struts will fail by crushing or squashing of the material. So the short column or stocky column will fail or fails by crushing of materials. And the slender column, it fails by buckling of the column. So let's now talk about the column design. I want now to talk about column design. So design of column or a column design. So Design of column is considered under the following. So number one, we have axially loaded column. Axially loaded column. Number two, we have axially loaded column with moment. Axially loaded column with moments. And number three, we have cased column. So I want to begin by axially loaded column. So number one, axially loaded column. So when a column is axially loaded, it means the load is at the center of the column. So the load is at the center of the column. So this, it means it is an axially loaded column. So a column supporting an axially load is subject to direct compression. So a column supporting an axially load is subjected to direct compression. A column supporting an axially load is subjected to a direct compression. So the compression resistance, the compression is given by this formula. So this is the symbol for compression resistance. So this is P, C is capital P. Compression resistance is given by PC is equal to AG. This is PC, this is small pc, and this is capital PC, whereby capital PC is equal to compression resistance. Compression resistance. And AG is equal to section area of the section. Section area of the section, and small pc is equal to compression strength. Like that. So to ensure that a particular steel column is adequate, its compression stress must be less or equal to ultimate axial load. So to ensure so you have said the compression resistance, which is PC, is equal to AGPC, like that. To ensure that a particular steel column is adequate, its compressive stress must be greater or equal to ultimate axial load. Ultimate axial load. And we can say that PC must be greater or equal to F, whereby this F is given by this formula 1.4 GK plus 1.6 QK. GK is the dead load and the QK is the imposed load. The compressive strength is influenced by the slenderness ratio. So the compressive strength is influenced by the slenderness ratio and is symbolized by lambda, whereby the lambda is equal to LE of R. So the LE is the effective length of column, and R is the radius of gyration. R is the radius of gyration of the section about the relevant axis of the section about the relevant axis like that. So the maximum slenderness ratio of steel column carrying dead load and imposed is limited to 180. So you can say here that PC must be greater than F, whereby F is 1.4 GK plus 1.6 QK, like that. then the slenderness ratio is equal to LE or R, whereby LE is the effective length of the column and R is the radius of gyration of the section about the relevant axis. So I have said that the maximum slenderness ratio, the maximum slenderness ratio of steel column steel column carrying dead load and imposed load is limited to 180. So mathematically, slenderness ratio must be less than 180. So slenderness ratio must be less than 180. So this is for a steel carrying GK and QK. But if you can include what we call the wind load, then we will have a different case. So the effective length LE depends on the end fixity of the column. So the effective length, which is LE, depends on end fixity of the column. So we have the effective length for different end fixity of the column. So number one, both end is fixed. So the effective length is calculated using this formula. This is 0.7 L, where L is the overall length of the column or the overall height of the column. And this statement is explaining this one. So the effectively held in position at both ends and effectively restrained in direction at both ends. So this is the case. So this is the column. So LE is equal to 0.7 L. We go to number 2. So we have number 2, and this is one end fixed and one end pinned. So the effective length is equal to 0.85 L. As you can see, this end is pinned and this end is fixed. And this is the effectively held in position at both ends, but restrained in direction at one end. So this statement is explaining this statement. So both of them are the same thing. So LE is equal to 0.85 L. So we proceed to number 3. So number 3, we have both ends pinned. So effective length LE is equal to 1.0 L. So it is effectively held in position at both ends, but not restrained in direction at either ends. So as you can see, these are the pinned, both ends are pinned. So it means the column can rotate in either side. So the effective length, which is LE, is equal to 1.0 L. And I have said L is the overall height of the column. So we have number 4, one end fixed, other end partially restrained. So the effective length LE is equal to 1.5 L. So one end effectively held in position and restrained in direction, and the other end not held in position but partially restrained in direction. As you can see, this one is permanently fixed and this one is partially restrained. So LE is equal to 1.5 L. We proceed to the last one, which is number 5. And the last one is number 5, which is fixed at one end and the other free. So the effective length is equal to 2.0 L. So one end effectively held in position and restrained in direction, this one, and the other end held in position but not restrained in direction. So LE is equal to 2.0 L. So that is all about the end fixity of different types of column. The value of compressive strength, which is PC, in relation to the slenderness ratio, and design strength PY is obtained from table 27A2D of BS 5950. With respect to universal column section, the particular struts to use is given as, so this is the table. We have the section type. This is the rolled section. We have the thickness of flange up to 40 millimeter. So the buckling along the XX axis will use table 27B, and YY axis will use 27C. Then we have over 40 millimeters. For the XX axis, 27C. And then for the YY axis, 27D. Failure of column is usually about y-axis, and the lesser value of the PC from the table 27B and C is used for design. Example,